like tons of people during office hours, so remember when those are. I'm happy to help you. Occasionally we'll have some time in class. I'm hoping maybe tomorrow we might have a few minutes where we can talk about some homework problems or any issues or something like that. But really, I mean, the I try and pack the lectures full of a bunch of examples so you can see lots of different types. But it's that practice and making sure you get those right. And some of the problems in the book are really hard, and some of them are not too bad. But I think you're seeing the further we go, you see all of those algebra and all of those pre-calculus and all of those trig skills cropping up again, and it's a lot to keep track of. So it does take quite a bit of practice. So let's take a look at this section right here. This is on differentiating logarithms. And what I'd like to do is just real quickly, let's just go through it and review some of the ideas that we've covered so far. So if I find the derivative of an exponential, so this is a general exponential, basis a, and the variable in the exponent is some function u that's a function of x. So the derivative of an exponential is that same exponential times the ln of the base times the derivative of whatever we were plugging in there. Okay. So if we apply that to this problem right here, we're going to have 2 to the sine of x times the ln of 2 times the derivative of what we were plugging into that exponential. So that's going to be times cosine of x. Might not be a bad idea to put that in parentheses, just separate that off. Or if you put the ln of 2 in parentheses, then that makes it a little bit more clear that that's just a factor there. Ln of 2 is just a number, okay? It's no longer a function, it's just a constant there. And then we could apply the same thing here. So the derivative of that exponential is that same exponential, ln of the base, times the derivative of whatever we were plugging in. And both of these turn into 1s, okay? So we just get e to the x, okay? Just like we're used to, all right? Well, let's run through for just a second because, again, what mathematicians do is we take tools that we've already learned how to work with, and then we tweak those a little bit, and then we come up with new concepts or new problems that we can solve with those. So everything kind of builds on itself. So let's think about the differentiation rules that we know so far. Okay, what was the easiest differentiation rule? Okay, so there was one. If we did f plus g, if we found the derivative of that, then that's just the derivative of f plus the derivative of g. That was pretty darn easy, even easier than that. The constant. So if I have the derivative of a constant, I get 0. Okay? And then we also had the constant multiple rule. So if I had the derivative of a constant times a function, it was just the constant times the derivative of the function, right? Okay, those are some really easy ones. So let's kind of step up the difficulty here. Let's see, we know how to, if it was add or subtract, so let me put a minus on here also. Derivative of a constant, constant multiple. What kind of came after that? Okay, quotient and the product. So let's do the product rule first. So if I had f times g, and now we're finding the derivative of that, that's going to be, okay, first times the derivative of the second plus the second times the derivative of the first. Again, it wouldn't matter which order. Each one gets its turn being differentiated, and then we add them together. Order is not a huge deal with the product rule because it's multiplication. We've got those commutative properties. Multiplication is very often associated with addition. Okay. If we do the quotient, though, that's a completely different story. Then I've got to do, and please make sure you have this memorized. I did run into a few people either on the representative problems or even on the quiz that we took that don't have this straight. It has to be in this order. It has to be the bottom times the derivative of the top. So that's going to be g f prime. Then it's got to be a minus f g prime all over the bottom squared. And if you do the low-d high, high-d low thing, that's all well and good, and it sounds nice and sing-songy and stuff like that. But if you don't know what low-d high means, you're in trouble. Okay? Low, bottom, d high, derivative of the top. Okay? That's how that starts out. Okay? Next. Okay, let's do the power one, because nobody forgets that one, right? You're going to know that until you hit your grave. So that's going to be bring down the exponent, reduce the exponent by 1. And again, we could make the base a function of x. So we could do a u here, and then times by du dx. And then we also had the chain rule. So f of g of x prime, that would be the derivative of the outside, leave the inside alone, and then times the derivative of the inside. Okay. What else have we got? What else have we learned how to differentiate? Okay, so exponentials, and let's write the general exponential like we did up here. A to the u prime, so that's going to be a to the u, ln of a du dx. So we've got that one up there. Of course, e to the x would fall in that category. That's one we've got memorized. That's the easiest one of all, probably. Okay, what else? Yeah, let's do trig functions. So let's just write an example. So let's say we do sine of x. Its derivative would be cosine of x, and then all of those related derivatives. And then we've got inverse trig functions. So let's say I do cosine inverse of x, and I want to find the derivative of that. Inverse trig function, it's got a cos, so it's going to be negative 1, and then it's a square root. Got to remember the order here. 1 minus x squared, okay? 1 minus x squared, okay? And then anything else? Yep, if you wanted to, we could do e to the x prime is just e to the x. And then there's one last technique that we haven't talked about. It actually made it possible for us to find the derivative of inverse functions. Implicit. We learned how to do implicit differentiation. Okay, again, treating everything as a differentiable function of x. Okay, so what we're going to do is we're going to take the tools that we've just talked about and reviewed, and we're going to find the derivatives of some new functions. And in this particular case, we're going to find the derivative of log base a. Okay, so we'll throw a number in there in just a second, like we're going to find the derivative of log base 2. But in order to find the derivative of log base a of x, we're going to use the tools that we already know. We're going to use the information that we've got. All of this stuff up here is available. Can we rewrite this? Like, I mean, do you know how to find the derivative of this? I mean, if I just put a problem like this on a test, do you know yet? Okay, we could write it as the log of x over the log of a, or use an ln or something like that. But then it's still in terms of a logarithm. So we're still stuck with the same problem. We've got to find the derivative of a logarithm. Okay, so what we're going to do is we're going to come back here and we're going to say this. We're going to write this as it's with respect to its inverse. So we're going to write a to the y equals x. And then we're going to apply what type of differentiation? I mean, it's got a hint right here, right? We're going to do implicit differentiation. So this is going to be a to the y, ln of a. Help me out here. Nope. dy dx. Okay, notice the uniformity here. We did this problem at the very beginning of class today, and look at the uniformity here. We're differentiating this with respect to x, so this is just going to be a dy dx, which really is what we're after here. Derivative over here, just, yep. Okay, so we've got a 1 over here. Now let's solve this. So here's what I've got. I've got dy dx equals 1 over a to the y ln a. Done? Yeah, I mean, we could leave it in terms of y, but it would be really nice since the original function was explicitly written as a function of x, if we found the derivative in terms of x. So what do? Okay, very good. So Zach's one step ahead of where I want to be. What we want to do is we want to replace the y, and then let's see what happens there. So here's what I've got. Let me slide this over. I've got 1 over, this is going to be a. What am I putting in place of that? Log base a of x, and then I've got this ln a right here. And where Zach jumped to was dy dx is equal to, well, the 1 isn't going to change. A to the log base a of x. What does exponential base a and log base a, what do they have to do with each other? What do they do to each other? They're inverses of each other. So what is this? Just an x, and that is an ln a, and right there is the answer. Now, what I'd like you to stop and think about is think about that confusing relationship that we went over with inverse functions. Okay? That little formula said in words, the derivative of an inverse is the reciprocal of the original function. Okay? So this would be 1 over, remember this guy right here? The derivative of exponential base a is exponential base a times the ln of a. So this is the reciprocal of the original function with the inverse plugged in. What's the inverse of exponential base a? Log base a. If you plug that in right there, they undo each other, and here is the derivative. So we could have done this problem the way we did approach those other ones. What's the function? What's its inverse? Find the derivative of the original function, do the reciprocal of that, and then just plug the inverse in. That's exactly what we did right here. Okay? So just like with exponentials, whose base is a, they've got this extra factor of ln a floating around here. That's what we've got on this one right here. We've got this factor of ln a floating around, and we'll see how this works in just a second, especially when we've got, let's see, we're going to do the ln in just a second. So let's take a look at this one right here. We would have 1 over x ln 2. If it's y equals log base a of x, if we get 1 over x ln of a, wherever there's an a, we're going to put a 2. So we put a 2 right there. And this was x, and that's x, so it's just 1 over x ln 2. That's it. That's simple. So if I find the derivative of log base b of x, it's going to be 1 over x ln b. So again, if we set it in words, it's just 1 over u ln a, if we think in terms of the chain rule and all that sort of stuff. So this would be 1 over u ln a du dx, if we wrote it in kind of a general generic form. Okay? Now, I think I mentioned before that for some reason logarithms are something that people struggle with, and exponentials that have a base other than base e. Okay? So let's run through and let's practice a couple of these. So let's take a look at this problem right here. Question? Okay, so all of these were just plain old x's that we were plugging in. We didn't even really think about carrying out the chain rule, but if we're plugging a function into a logarithm, you've got to find the derivative of the logarithm, so that's going to be 1 over whatever we were taking the log of, times the ln of the base, times the derivative of whatever we were plugging in. So let's take a look at this guy right here. This is going to be 1 over whatever we were taking the log of, so that's going to be 5x, or sorry, 5 theta in this case, ln of the base, so ln of 4, and then times the derivative of whatever we were plugging in. Notice we've got a 5 theta here, and we're differentiating with respect to theta, so I put a 5 here. And then we'll clean this up just a little bit. I'm going to cancel those, so I end up with 1 over theta ln 4, and that is my answer there. Logarithms have always got that 1 over thing going on, so we do 1 over whatever we were taking the log of, so that's going to be, x squared plus 1, or excuse me, plus x, times the ln of the base, and then times the derivative of whatever we were taking the log of. So this is going to be 2x plus 1. Can't cancel anything. It's factored completely and stuff like that. I suppose I could take out an x, but that's still not going to make something that I can cancel with. So we're going to leave this as 2x plus 1 over x squared plus x ln of 3. And again, take note of the fact that when you've got an exponential base 3 or a log base 3 and you find the derivative, we're going to always have that factor floating around of an ln of 3. When it's a logarithm, it happens to be in the denominator. Okay? And we'll look at a couple other ways you can tell that that's got to be the case. Question? What's that? It is. Okay? So Juan's got the answer to this, but if we follow the technique here, the technique is it's 1 over whatever we were taking the log of, times the ln of the base. And what is the base of the natural logarithm? E, okay? And then times the derivative of whatever we were plugging in. And again, see the uniformity here? E is a very special base, whether it's the base of the logarithm or the base of the exponential. Okay? So the rule works here. We get a 1 here, and this is a 1, so the answer is what 1? 1 over x. That's it. Okay? So the derivative of ln x is just 1 over x. Derivative of ln x is just 1 over x. Okay? So if we think about this in terms of the chain rule, the derivative of ln u would be 1 over u du dx. Or if you wanted to use u prime, which I think this book is a fan of u prime, let's think about this. This would be 1 over u times u prime. Wouldn't this just be u prime over u? 1 over u times u prime. Multiply those together. U prime on top, u on the bottom. I'm not a huge fan of that, okay? But it would be kind of a little shortcut if you wanted to think of it that way, okay? Any domain issues when we're talking about logarithms? Okay, you can't take the log of 0 or negative, so you do have to be a little bit careful. Whatever was plugged into this had to be positive, okay? And usually it's not an issue. I mean, whatever the domain was for the original function, depending on exactly what it's configured of, is going to be the same as the one for the derivative, but be a little bit careful with that. So let's take a look at a couple of these examples right here. So we've got the ln of x cubed. So the derivative there is going to be 1 over x cubed times the derivative of x cubed. So that's 3x squared. So I'm going to cancel this with that. So y prime in this case is going to be a 3 on the top and an x on the bottom. Let's take a look at this next one. What rule? Product rule here. So we're going to do the first. Sorry about that. There we go. So we'll do the first times the derivative of the second. So that's going to be 1 over x plus the second times the derivative of the first. And the derivative of the first is 2x. Do a little bit of cleanup. So I'm going to have an x here plus, how would we normally write this? Yeah, we're going to move that out as if it's kind of like a coefficient. Okay. Questions? Okay, let's take a look at the next one then. S prime is going to be, and we're differentiating with respect to t here, so it's an ln. So it's 1 over whatever we're taking the ln of, so that's going to be a tangent radical t. We don't have to worry about multiplying by ln of the base down here because the ln of e would be 1. We're going to find the derivative of whatever we plugged in here. And again, you can look here, or sometimes it's better to look here. Remember, we're using the chain rule here. We're peeling this off an outside function at a time. So I found the derivative of the outside function ln. Now I'm to tangent. Derivative of tangent? Secant squared radical t. Now we're finally to the very inside. The very inside is radical t, and that derivative is 1 over 2 radical t, right? Can I do any cancellation here or anything like that? We could write this in terms of sine and cosine, and maybe that would clean it up just a little bit. Probably not worth it. Maybe it is, maybe not. But I think if you looked in the back of the book on a problem like this, they'd probably show this. Probably the 2 radical t out front, and then the tangent radical t here. And then again, do we have to be careful about this in terms of domain or anything? We do have to be a little bit careful, so let's talk about this for just a second. What type of numbers could you plug into the original function here? Only positive numbers, okay? Okay, let's take a look at its derivative. The derivative looks like you could plug in negatives, doesn't it? Okay, but remember, if the domain of the original function, if this only exists for 0 forward, not including 0, the domain for this is going to be from 0 to infinity. Okay? Let's think about this one right here. Even though you can plug anything you want into x squared, we're still restricted to only the positives, okay, from 0 forward. And that doesn't change here, so this would be 0 to infinity. Let's take a look at the original function here. Let's think about tangent for a second. You can plug anything you want in that's 0 and bigger here, right? That would be okay. Yeah. Because you can take the square root of 0, and you can take the tangent of 0, can't you? Tangent of 0 is? Tangent of 0 is 0. Okay? So kind of working from the inside back out, okay? Could we take the ln of whatever we get when we plug in a 0? Nope. So that's going to be 0 forward on this one also. Okay? And do we run into any issues here? Good. Can I plug in a 0? Okay. Couldn't to begin with, and can't in the end there either. Yeah. Oh yeah. Oh yep. Okay. So let's throw these in. So it would be 0, and then let's throw out. So we do need to throw out the asymptotes, right? So we'll do k. Let's see. So we'd have to do pi halves. Thank you for pointing that out. And then they repeat every. Make some space here. Let's see. Pi halves would be our first asymptote, and then they repeat every pi units, right? Ooh, very, very good. Yeah, that'd be pretty funky, wouldn't it? Okay, we'd have to be really careful with this, because what comes out of this, okay, we'd have to have like the square root of t not equaling pi halves or any k pi multiple of that. Be a bit of a mess, wouldn't it? Okay, worth worrying about? Probably not here. Would I ask you that on a test? Maybe a bonus question, but only for Juan. We'd make him do it. Okay? All right. What's that? Did you really? Okay. Okay, we'll ask everybody that question in Maddie's honor. Okay? All right. So let's take a look at these last couple of problems. And I added these little hints here on these. So I've got an A star and an A double star on this one right here. Let's figure this one out using a property of logarithms. So we're going to do it two different ways. So any suggestions, Peter? Okay, what property is that? What's that called? It's that thing deal, right? Power property. Power property. Okay, so I can slide that out front. So I can write this as 3 times the ln of x. So y prime would be, this is a constant multiple, so this is going to be 3 times the derivative of ln x, which is 1 over x, so I get 3 over x. I get the same thing that I got right there. Is there another property of logs that I could do and produce the exact same answer? Power property. Logarithms have these awesome properties where they make computations simpler, so we can take an exponent, slide it out front, and use it as a factor. Logarithms have this ability yet. Very good. There we go. So we're going to write it as ln of x times x times x. This is now a multiplication problem, and logarithms have this unique ability to change multiplication problems into addition. So this would be the ln of x times the ln of x, or sorry, plus the ln of x, plus the ln of x, okay? Which, if you think about it, if you go back to what you learned in your 1010 or 1050 class, I guess 1050, that's where this comes from, right? Repeated multiplication is repeated addition, so you can make that into multiplication. So this would be 1 over x, this would be 1 over x, this would be 1 over x, so that means y prime is 3 of those guys, so 3 over x, okay? So 3 different ways to accomplish the same thing. Questions there? Okay, so with that in mind, let's think about this one right here, and there might be a couple different ways that we could consider this. log base 4 of 5 theta. We already know what the answer is. We did this one up in example 3. Is there another way you could get the answer using properties of logs? Log base 4 of 5 plus log base 4 of theta. Wouldn't that work? So what's the derivative of log base 4 of 5? As ugly as that is, Peter says it's just a constant, right? So what's its derivative? 0, okay? And what's the derivative of log base 4 of theta? That would be 1 over theta ln 4. So our derivative would just be 1 over theta ln 4. Good there? Okay. Hold on. Take a look at this. Again, it's pretty awesome when things have lots of different ways to write them and work at the answer. There's one property of logarithms that we haven't used yet that, I mean, if everything works perfectly together, we should be able to rewrite this using change of base formula, okay? Let's change the base, okay? Let's change it to the natural log. So if I write this as the ln of x over the ln of 2, which you can do with any logarithm, including this one right here, this would be the ln of x over the ln of b. And then I find the derivative of each one of these. I've basically got a constant floating around here. I've got a 1 over ln 2, and then I'm going to find the derivative of ln x. Make it look like a prime. So that's going to be 1 over ln 2 times 1 over x. Or probably the easiest way to write it is 1 over x ln 2. And then the same thing here. So this would just be 1 over ln b times 1 over x. And we'd write it like that. Okay? So all of those properties work perfectly together. Any questions? Okay. So now we're going to talk about something called logarithmic differentiation. Okay? And it's usually used in one of two cases. Okay, when we're trying to find the logarithm of a really ugly expression, and taking the logarithm of both sides would make finding the derivative easier. So you'll notice that this right here is a product, a quotient, and a chain rule. We'd have to use the chain to find the derivative of the x plus 1 to the 5th. Okay, definitely have a quotient here, and I've got a product on the top. Logarithms have a nice ability to kind of separate those using the properties of logarithms. Okay, or this is where it comes up a lot, when we have a function of x raised to a function of x. Okay, and I'll be honest with you, on an example like this, like on 5a, I don't find this a heck of a lot easier. Okay, so here's what we do. This is an equation, so we're going to do some algebra on it. I'm going to do the ln of y equals the ln of all this stuff. And then what we're going to do is we're going to say, well, look, this is division, a product, and a power. So remember those problems in your 1050 class where you took this and wrote it as a bunch of different logarithms and wrote powers as factors? That's what we're going to do here. I'm going to take this and I'm going to write it as 5 ln x plus 1 plus ln of 3x plus 7 minus ln of 5 minus 2. Oh, 5x. Yeah, thanks. Good there? Okay. Okay, I'm going to cover this up right here. Pretend you can't see that. So this side equals this side over here. Okay, all I've done so far is just algebra. Now let's do some calculus. So this side, implicitly differentiated, would be 1 over y dy dx. And over here, I would have Well, let's see. This is a pretty simple function to find the derivative of. It's just 5 over x plus 1. Constant multiple. 1 over whatever I'm taking the ln of times the derivative of whatever I'm taking the ln of. So the derivative of x plus 1 would be 1. Everybody okay with that? Want to see more work, or are we good? Okay, let's take a look at the next one. The derivative of ln 3x plus 7 is going to be 1 over 3x plus 7 times 3. So let's put a 3 up here. Oops, minus, thank you very much. Minus 1 over whatever we were taking the ln of times 5. So I'm going to change that to a 5. Depends. I don't want a 1 over y on this side, so what would I do? Times both sides by y is what I do. Okay, so here's what I get. I get dy dx equals, this would be y times, and then in a big set of parentheses, I'm going to write this stuff here. Oops. Yeah, so let's do this. X plus 1, 3x plus 7, 5x minus 2. What would we have here? Okay, well, stop for just a second. Let's think about this for a second. Are we going to leave it like this? Do we plan to add these together, get a common denominator and all that sort of stuff and leave it like that? What would we normally do with that, with the y? We could multiply through by y, or stop and think for just a second. Let's not get too far down here. What would we normally do with this? Every time we've done this, every time we've done implicit differentiation and we've had this reciprocal thing and then we've moved things around and solved for dy dx, what do we normally like to do? Yeah, put what y equals. Okay, so let's come back here and let's think about this for just a second and see if this has an advantage for us. Okay, I'm going to make some space right here. Okay, and I'm going to multiply by what y equals. What y equals is x plus 1 raised to the 5th, 3x plus 7 over 5x minus 2. Okay, would that help at all, having it like that? What would happen if I distributed through now? I can cancel one of these with one of those, and then there's just a 5 on the top. Okay, the 3x plus 7 would cancel there, and then I'd have a minus 5 times this stuff, and then I'd have 5x minus 2 quantity squared on the bottom. Okay, okay, but consider what I've got right here. Take a look at it. Was this hard right here to rewrite it? Was this hard to get that derivative of each one of those terms there? And all we did was we had 1 over y dy dx, and I just multiplied both sides by y. So what I've circled right here, could that serve as the answer? And would it be that hard to plug a number into it? Okay, main point here. Do I have the derivative? Am I done finding the derivative? Am I done with calculus? Yes, I am. Consider what the alternative is. So let me bring this back here for just a second. Or I guess we're looking right here. What rules? Quotient first, a product within the quotient, and a chain rule problem. Okay? Instead, we rewrite it this way. Find the derivative of each piece, put that in a big set of brackets, slap what y was in front of that, and we have the derivative. Not a nice derivative. It looks like a pretty ugly mess. Okay? I'm not a huge fan of this. I really don't mind going through and finding the derivative using the quotient rule, the product rule, and the chain rule. It actually doesn't turn out to be that bad. I mean, it's pretty ugly either way. Okay? Logarithmic differentiation, one application of that. okay? Ugly problem no matter what you do, okay? Let's take a look at a different type of logarithmic differentiation. Same format, the same types of things are going to happen, but algebraically this is going to be a heck of a lot easier, okay? And I want you to consider what type of function this is, okay? This is not an exponential, okay? An exponential is a number raised to a variable, okay? That's an exponential. It's also not a power function. A power function is a variable raised to a number. So that's not a power function, and it's not really an exponential. Okay? The name we usually give these, we call these super exponentials, when the base is a function of x and the exponent is a function of x. And what we do to evaluate these is we do this. I've got to get this exponent down where I can work with it. I've got to turn this into a tool that I already have. So watch what happens if I take the ln of both sides. If I take the ln of this side and the ln of this side, it looks like I've made it more complicated, but watch. I can apply the power property. So I've got the ln of y equals x ln x. And now differentiate. What type of differentiation? Implicit differentiation. Look at that 1 over y dy dx. Happens every time when we've got a log ln of y. Then it's going to be the first times the derivative of the second. Look how cool that is, the way that's going to work out. Then the second times the derivative of the first. So dy dx in this case is y, and then in brackets I'm going to write what we get here when we were finding the derivative. So this is going to be 1 plus the ln of x. And then let's bring back what y is. Y is x to the x, okay? So y prime in this case is going to be x to the x, 1 plus the ln of x. There's our answer. Let me see if I can remember. We've used a book at the college before that uses this identity right here and shows, yeah. What?
Isn't it times ln of x, or?
What do you mean? Here? Right here?
Oh.
So the question is it times? Yeah, it's times right here. So what I did to differentiate this side is this is the first and that's the second. I used the product rule. First times the derivative of the second, second times the derivative of the first.
Yeah.
Good? We okay? Okay. So it's possible to use this identity right here. I'd like to go through and do one more using this other technique. So again, if I find the ln of both sides, that's going to slide out front, so that's going to be the cosine of x times the ln of x. Ln of y, implicitly differentiated, is going to be 1 over y dy dx. Again, uniformity happens the same way every single time. And then Weston, what do I do here? Product rule here. So this is going to be the first, and that's going to be the second. So we'll do the first times the derivative of the second, plus the second times the derivative of the first. So when I write this, again, we've seen this a couple of times now. I'm going to move that y to the other side by multiplying by y. So it's y equals, and then I'll start a set of brackets, cosine of x over x minus sine of x, and then I'll start a set of parentheses, ln of x. Okay, and this pattern happens every single time. We've always got this y sitting out in front of what we found the derivative of here. So y in this case, I'm going to go ahead and replace that, is going to be x cosine to the cosine of x. Could we clean this up a little bit? I mean, I suppose you could do this, x to the cosine of x, and then here, let's get a common denominator. Let's put everything over x. So this would be the cosine of x minus x sine x ln x. Again, make sure it's, whoops, let's make sure that it's clear what we're taking the sine of or the ln of, that would be okay there. Okay. If you had one of these on the test, I'd consider that simplified to a reasonable degree, but not a big deal either way. Okay. Any questions? Okay, let's take a look at the last couple of problems here. And let's try problem number 44, only let's use this identity right here. We talked about how you can write any exponential as an exponential base e. We talked about why this is an identity, and let's think about this for just a second. The reason it's true is because if I slide this up here, I have e to the ln of u to the x. These would undo each other, so I would have just u to the x. But let's consider this guy right here, and let's rewrite this using this idea right here. So the base here, the u part would be x. The exponent part on this problem right here would be the cosine of x. So if I was going to write this as e to the x, that's going to be the cosine of x is taking that place, and then this is going to be the ln of x here. Take a look at that and see why that identity works the way it does. I just rewrote this right here that way. See why it works? You could just slide the cosine up here. It would be e to the ln of x to the cosine of x. The e and the ln would undo each other. We'd have x to the cosine of x. Okay. Why is that advantageous? Because we know how to find the derivative of exponential base e. And what is this up here? How would I differentiate what we plugged into the exponential? Weston? Since it's this times this, it's a product, okay? It ends up being the same thing that we had here. So what I have is the derivative of e to whatever is e to whatever times the ln of whatever we were plugging into the exponential. So that's going to be the first times the derivative of the second plus the second times the derivative of the first. And that looks really familiar. And what is this right here because of that identity? Yeah, this right here can be replaced with e to the cosine of x. So if you take those guys together, you've got our answer right there. Okay? I'm not a huge fan of that. I didn't learn that way, and maybe that's my bias, but it is an interesting technique, and it's a cool use of that identity. Okay? It also kind of emphasizes how important exponential base e is. I mean, gosh, we turn logarithms. We can think of all of those in terms of natural logarithms by using the change of base formula. And using this identity right here, we can take any exponential and write it as exponential base e, which generally speaking, those derivatives are a little bit easier than the other ones. Okay? All right. Any questions? Okay, let's take a look at this last little bit. Again, a hint for number 56. Sometimes taking the natural log of the expression can make finding the limit a little bit easier, just kind of like logarithmic differentiation like we've been showing here. And I want to take a look at each one of these. Take a good look. This is just to check and see if you're paying attention here. What would the derivative of a to the b be? Yep, because that's just a constant, right? Take a look at the way this is set up. Think about what rule applies here. What type of function is this? This is a power function because the base is a variable expression and the exponent is a number. This is a power function, so its derivative would be n u to the n minus 1 du dx if we were finding the derivative. We could write u prime if we wanted to. Maybe that would be better. Times u prime. What type of function is this? Nope. It's an exponential. Remember, the base is a constant. The exponent is a variable expression. Okay? This is the one that we started class with. the derivative of a to the u, the derivative of exponential base a. So this is going to be a to the u, ln of a, okay? And then we'll do times u prime, keep with the prime notation. Try and write mine a little slanted so it looks like a prime. And from what I understand, I'm hopefully getting a new projector in the next couple of days. So hopefully this looks nice and bright, okay? Yeah, I don't like the tilt either. Okay. All right. What is this? Super exponential, okay? It's a function raised to a function. So if we were going to find its derivative, gosh, could we think about how to do that? Could we come up with a rule for that? Let's look back here. How did all of these turn out? Look at the function to start with, and look at what we ended up with. We ended up with x to the x. It was x to the x and then 1 plus ln x. And here it was x to the cosine of x, and it was x to the cosine x, and then this stuff in here. Really maybe better to look right here. What's this going to turn out to be? Okay, it is going to have a u to the v, and I'm going to make myself a little bit of space. U to the v, and then in parentheses we're going to have, anybody know? Yeah, it's going to be the product rule, and think about what happens here. If I did an ln, the v would be out front, and the ln of u would be right here. And then we'd be finding the derivative of that using the product rule, right? Does that make sense? Okay. Now, is this rule worth memorizing? Weston thinks it is. I probably wouldn't, but it's just kind of interesting that for whatever pattern, whatever differentiation technique we come across, we can usually come up with a formula for it. So this is going to be v 1 over u prime plus ln of u times v prime, okay? And if you think about it, and I'm sure somebody's going to go home because we're all completely nerdy about this, you could go home and you can check and see, gosh, would this work on this stuff that we did up here on 40, what was that, 40, 43 and 44, okay? Okay, so take a look at that last one. Nasty mess right there. Okay, don't worry about the algebraic simplification. Could you go through and do the calculus to find the derivative there? Try that right now. We got a couple minutes left. No, just find the derivative there. Think about the rules that have to apply. Darn those trig functions. I'm not differentiating. I'm just rewriting. Okay. I mentioned before that sometimes it's helpful to write, if you have a trig function that is raised to a power, and we normally write it right there without parentheses, a lot of times it's helpful to rewrite it so that it is in parentheses so that you can look at it and you can say, oh, I can see what functions I'm dealing with here. Okay? So let's see. What would I do? Quotient, okay? Got to use the quotient, okay? That's, in the big picture, that's the first rule that would have to be applied. Next, product, because when I'm finding the derivative of the top, I've got a product. And after that, chain. A couple of chains to apply here, okay? I've got the fourth power function, I've got the secant function, and then I've got x squared there, okay? See if you can finish that off, okay? Don't worry about the simplification so much. I probably would not give you something quite that ugly, okay? But you could definitely have one on the test that has a quotient, a product, and a chain, okay? Maybe not quite as many chains, and maybe not with a trig function, okay? Because those get a little bit hairy, okay, depending on which one it is in particular, okay? But hopefully you can at least do the calculus and at least set it up. check with your neighbor, see if you got it. Okay. All right. Any questions? All right. Have a great day. If you've got questions, feel free to stick around.